Thank you for being here today, and thanks, James Quach, for the invitation. So I'm from RMIT University, which is here in Melbourne, Australia, and I'm going to talk to you about a study that we did on metal nanoparticles and how to extract energy from sunlight using said particles. So when you think about solar power, most of you will naturally go and think of photovoltaics and solar panels, and that's actually still a field of research and worthwhile effort to generate sustainable sort of means of power and power generation. However, as of 2015, most of the power that we use is not in the form of electricity. In fact, we do still need to use chemical fuels, and this is because mostly for transportation. All right, electricity only accounted for about 20% of how we use energy. And most of that energy is actually used for, as I said, for transportation of goods. There is another way of using solar, and that is to generate these chemical fuels directly, or also for generating or producing fine chemicals that we normally use. These fine chemicals include things such as pharmaceuticals, or the inks or dyes that we use for the clothes that we are wearing. The field of using solar for doing chemical transformations directly has academically increased exponentially, as we can see by the number of publications, but it's also an industrial reality. This is a picture from Merck Chemical Industries, where they use compounds such as this one here is a metal organic compound that absorbs strongly visible or visible light, and it's able to generate electrons and holes pairs with enough chemical potential to do chemical synthesis, in particular for fine chemicals. The problem with using most of the most efficient sort of photochemical materials are wide bandgap semiconductors, and because they have a wide bandgap, they can only absorb blue light, which is a tiny fraction of the total incident solar power. What I do in the lab is that we create, I have to go back, sorry. We use metal nanoparticles as the light absorbers and catalytic sites. The reason being that metal particles have a huge cross-section for optical absorption, about 1 million times of the best molecular system out there. So a metal nanoparticle, when it absorbs light, it can create what's called a surface plasmon excitation, which is a collective oscillation of the surface electron in the particle, right? So if this is a particle, most of the surface, when light irradiates the particle, the charges in there will oscillate, and there is a resonant frequency that is dictated by the geometry of the particle. Once this energy hits the particle, the energy of the excitation can decay via Landau damping, a quantum mechanical process whereby all of the energy goes into the generation of an electron and hole pair. If the particle is sitting in something like in an inert chemical environment, all of that energy ends up being converted into heat. However, if one is clever enough, we can put the particles in a chemically reactive environment. And my collaborators and I, both in Japan here and in Australia, we have used this concept for doing water splitting, so that is using the metal particles to generate hydrogen, or also for the generation of fine chemicals such as the one that I briefly showed there, sorry. Another process that can happen with metal particles is that one of chemical interface damping. That is, if your particle has something attached to it, a chemical, once the photon hits a particle, it is possible for this particle to inject an electron into said absorbate. Why is that important? Because an electron, as it goes into a chemical, can initiate a chemical reaction. So you have converted an incident solar photon, and you have initiated a chemical reaction. So that is the core of my talk, and I'm going to now go into specifics, which are probably a little bit more detailed. So bear with me. This process, the one that I showed here, not long ago, gathered a lot of attention in a science paper by Professor Tim Lian. And the reason why is this number here, 24%. So that is a high in this field a super extremely high efficiency of conversion of photons into said electron and hole pairs. And he did that by creating a semiconductor rod with a tiny little metal particle. The particle absorbed the light and generated these electrons in the semiconductor. However, very importantly, not so much on the media, the same group, same structure, different chemical composition, 4% efficiency. So there is a huge gap here in terms of performance, and they didn't go into why that was the case. And so that is what we set out to do in the lab. And as a model system, we created a metal nanorod made out of gold, tipped with a semiconductor quantum dot, in this case, cadmium selenide. So the rod is going to act as an optical antenna that will harvest light and direct electrical charge into the cadmium selenide, the idea being that this can be used as a photocatalyst for the conversion of incident solar light into chemical potential energy. Briefly, we grow these materials using colloidal chemistry. That is, we use solution-based approaches with water, salts, metal salts, and precursors. We first grow the metal nanorods, and then by carefully tuning the chemical conditions, we grow the tips of the semiconductors on the one end of the rods with high fidelity. As in 90% of the product is the intended sort of structure, and we have done a lot of characterization. There is heteroepitaxial growth. As you can see here, the crystallographic planes of everything sort of seems to match very well. So these are actually nanocrystals, not just random particles. To characterize the process of conversion of plasmons into charge-separated states, we use electron microscopy in the form of electron energy loss spectroscopy. So with this technique, we image the structures. We get access to the geometry and composition of such structures in the electron microscope. We then use the electron beam as a localized broadband energy source. And the advantage here is that the electron beam is way smaller than the actual particle. So we can park the beam around the particle and actually map out where the energy goes as we excite the particle with the kinetic energy and electric fields of the electron beam. So we can measure the energy lost by the electron beam as it travels through the specimen. And this energy lost is actually not lost. It's transformed into the plasmon resonances in the nanostructures. From this experiment, we can record intensity maps, as in where is the energy lost more predominantly across the structure. And we can also get spectra. From the spectra, the line width is the actual sort of the key parameter here, as this is the homogeneous line width, which is related to how the actual sort of coherent oscillations of electrons, the plasmons, are losing energy via these dissipative processes. All right, so this is the part of the talk which is all about the data. I'm going to go very briefly, and I'm happy to talk about this in more detail in our launch time. So we start with a gold nanorod used to set up a control. With the electron beam, we get images. And as you can see here, the image has intensity, a strong intensity at the end of the rod. And that is because if this is the rod, what's happening is that there is a longitudinal oscillation of surface density. This is the longitudinal plasmon band. The other one is the transverse plasmon band. And you can see that that corresponds to two peaks in energy loss, shown here at around 1.5 electron volts. An important thing there for us is the line width of the spectrum, because that tells us how fast is that energy or oscillation damped in the system. As a further control, we grow gold on gold to achieve the same geometry as our target structure, just to test if the geometry plays a critical role in the process of damping. We get the same sort of set of data. From this data, we again get the line width. And here I'm plotting the line width as a function of a parameter that it's the average distance of any point along the structure to the surface of the structure. So the line width can be decomposed into contributions due to the chemical composition of the metal. So for example, silver will have a very narrow line width as opposed to gold or copper. Copper will be much stronger, and this is due to electron and phonon coupling in the structure. So how easy is for the electrons to be scattered by the nuclei? The second contribution is due to radiation damping. As I said before, for the nanorod, there is a longitudinal dipole longitudinal plasma oscillation. This has a strong dipole moment, and as a consequence of that dipole, there will be a lot of radiation scattering or relative scattering from the particles. This radiative damping is what leads to the beautiful colors of metal nanoparticles. This radiative damping is proportional to the volume V of the particle. So larger particles would have a strong radiative damping. The next term here is surface scattering. So processes that take place along the surface of the particle that lead to plasmon damping. So if the electrons are oscillating and all of a sudden they get trapped at one end of the surface, then you'll get a lot of damping. This damping is proportional to the Fermi velocity of the electron, it's the surface charge density of oscillation, and it's also dependent on the average distance of the electrons to the surface of the particles. So as you can see here, most of our experimental data sort of sit along the line, the black line of the model, and there is not much difference between the rods and the rods with a bigger cap. The bigger cap is only changing the average distance of the electrons to the surface. All right, now we grow the cadmium selenide quantum dots on the particles, and we repeat the experiment. Again, this is what the data sort of looks like. Contrary to the bare rod or the metal nanorod results, we see here that there is more intensity of the signals at the end where we have the metal alone, and there is, by comparison, a strong damping of the oscillation near the quantum dot region of the maps here. This damping is manifest as an increase in the average line width, and we contend that this is due to interactions between the metal particle and the quantum dot that we have grown onto it. We repeat the analysis where we try to plot the line width as a function of the effective path length, and now the data for the gold cadmium selenide is shown here with the orange dots. It doesn't fit into the original sort of understanding of plasmon damping, and there must be, therefore, a new sort of interaction. So to sort of model this, what we did was to think of the whole process as some sort of like a random pool game where we come in with the white ball and we kick an electron from the tip of the rod. When we park the electron beam here, we kick an electron out, and we count, as a function of this escape cone, what is the probability that this electron will reach the surface. There are a number of other approximations we have done. This is just to see if this is similar to reality. And by just doing this geometrical analysis, we get a model that nicely reproduces the data. Not only this is satisfying, but the model depends here on the geometry of the particle and is giving us sort of like a further insight into how do we make the particles that best result in the conversion of photons to electrons. So to quantify the efficiency of the conversion of photons to electrons or photons to potentially chemical reactions, we came up with a quantity that we called the damping quantum yield. And at the time of submissions, our reviewers were extremely critical of us using this word, and we relabeled it as quantum efficiency because we are not really quantifying the number of electrons versus the number of photons. But anyways, this is related to the increase in the line width that we measured with the quantum dots relative to the line width of the plasmon band with just the metal particles. This is related, again, this allows us to compare our data to the data by Professor Tim Lian. Remember, he reported a 24% yield. That was groundbreaking science paper. We are now reporting that by some of our particles, we get at least double the amount of efficiency, up to almost 50%, which is quite encouraging, in particular, but because because our data allows us to identify what happens here in this data point in terms of composition and geometry and quality of the metal to semiconductor interface. The data here, as you can see, collected over many particles, is sort of scattered when we plot the quantum yield versus the average distance of the electrons to the surface. So we fed this data into sort of like a machine learning classification algorithm that will allow us to sort the data into at least, according to the algorithm, into at least 5 clusters, which the advantage of doing these experiments on the electron microscope is that for every data, we can go back and get information, as I said before, on composition, geometry, and quality of the interface. And what we found is that points here in the purple are those ones that correspond to having a short gold rod, small cadmium selenide tip, and a very almost perfect interface in terms of how heteropytaxial it is. Surprisingly, what we found is that the best overall results happened whenever our chemistry failed. And instead of producing a tip, it produced a cluster of very tiny metal nanoparticles, quantum dots. As to why that is, I am not too sure. So far, the electron microscope gives us 3 minutes, yep, gives us insight into the line width. So what we measure could be the consequence of energy or charge transfer. So we did an experiment in the chemistry lab where we used this salt here that has platinum, and we mixed this with the particles and illuminated the system. If there is electron transfer from the metal into the semiconductor, this electron could be taken up by the platinum salt. And if that was the case, then platinum could deposit via a photoredox chemical reaction. If that were to happen, then we will have platinum deposition here. And in the electron microscope, there is a very strong contrast between platinum, gold, and cadmium selenide. So we did the experiment. Then we brought the sample back into the electron microscope, and then we did single particle imaging, but this time we were mapping for the presence of platinum. And as you can see here, platinum tends to accumulate first at the interface, giving us confidence that we are measuring electron transfer from the gold rod into the semiconductor tip. And we do that with over 40% quantum yield. So we are sort of leading the field in the area of converting incident photons into electrochemical potential using metal semiconductor nanostructures. And that brings me to the end of the talk. Thank you so much for listening.
Any questions for Daniel? James?
Thanks, great talk. I know this is a tough question, but so your magic particle, the 50% one, any insight into how to make that one with the clusters instead of a single?
With the clusters, yeah, as I said before, that was luck. Not the intended product. It just happened to be there, and we just imaged it. But I have no idea. I suspect that maybe higher temperatures during the growth can help.
Are you trying to make a homogeneous solution of that particular?
I would, but the student just finished her PhD.
Any other questions? So just on the point of the homogeneity, so when you do those measurements, you get a batch of different length ones and you analyse each one individually,
Yes,
is that right? So
correct, yep.
you get the effective length.
Yep.
over that whole ensemble.
Yes, and that's the beauty of the electron microscope as well. Even within a single batch, there are tiny variations in particle size, and we actually look into that as well.